system. And well, that was fine for a first order system. That was a CSTR was really a first order system. It was interchangeable. We saw a second order system. You could build some second order systems by taking two first order ones in series. But that was a special case where we saw that G only had real roots. That is, the denominator only looked like this. So the roots where S is minus 1 over T1, or S is minus 1 over T2. With T1 and T2 are real positive numbers. So the roots were negative and real, in which case the system is overdamped. That is just decays exponentially to where it's going. We saw, however, that that wasn't the most general second order system. A more general second order system allowed the coefficient of S. When I multiply this out, I get a quadratic. It allowed the coefficient of S in the quadratic, whereas here it would just be T1 plus T2. Here it allowed it to be arbitrary with some number C, where the only requirement was that C had to be positive, non-negative. We went through and we solved this case, and we saw that as long as C was positive, was greater than 1, everything was still overdamped. But when C was equal to 0, then we had no damping at all, and like with the block on the spring, we just got simple harmonic motion, sines and cosines. And if C was less than 1, then the discriminant was negative, and we would get complex roots, but still have the real part be negative. And in that case, the system would be underdamped. It would oscillate and decay. And we wrote in particular what G tilde was for that case, as well as then the amplitude ratio, which is the magnitude of G tilde by omega, and phi, which was the arctangent, the imaginary part over the real part. And we noted that this special case, we could actually solve for what C would be in this special case. And we solved for it. It was on the blackboard. And in fact, we showed that for this special case, C was greater than 1. So, and that's why, so everything's perfectly consistent. When C is greater than 1, the system is just overdamped. It just decreases exponentially, which is what happened here. I also remind you that we did a similar calculation for the plug flow reactor. The plug flow reactor was just a delay. A plug flow reactor with no reaction. It was just a delay. And so it was e to the minus st was G tilde. And the amplitude ratio was 1, and phi was just equal to minus omega t. So that was the situation for those. And at the end of the hour, and if you remember, all of the situations that we had leading up to the last hour, all the specific cases, first order, second order, CSTRs, the room heating where there was conduction through walls, all those situations, when we wrote them out, they were all of the form a derivative of the dependent variable plus a constant times the dependent variable equals some stuff on the other side, some forcing. And the question was, what was the significance of that constant times the dependent variable? What was the mathematical significance? Physically, we knew what it was. It came from the model. But mathematically, what we saw is, if you brought it to the other side of the equation, if you have dy dt plus ay, if you bring that to the other side of the equation, that's dy dt is equal to minus ay plus the forcing function. So that says when y gets big, it decreases the derivative. So somehow it's a balancing. It drives the system to something more stable. If y gets too big, then dy dt has a minus y and minus ay on the other side. So if it gets too big, then the derivative goes down. Similarly, if it gets too small, then it goes down. Then the derivative starts going up because if it's y prime, then if y prime is negative, then dy prime dt is positive. What happens when you take that away? When you take that away, you get this integrator. So here there's no ay prime here. And in the integrator, we saw something different. In an integrator, we saw when I don't have an integrator, in the situations we had before when we had an ay prime here, then if we had a step function input, eventually the output reached steady state. If you remember, if we had a step function in the inlet flow rate or in the concentration of the inlet, eventually the outlet reached steady state. It didn't go as a step function. We saw if the input went as a step function, then the output, if it was a first order system, went as 1 minus an exponential. If it was a second order, it went a little smoother. Third order, it would go a little smoother, but eventually it went to a steady state. On the other hand, what you see here in the integrator, when I don't have that, then if I have a step function change in the input, then the output just grows. It integrates. Because when I integrate this equation, I integrate the change in x prime. So if x prime is a constant, goes to a constant, then I'm integrating a constant, it increases linearly. So that's why we call this an integrator, rather than, and it doesn't have that plus a y prime here that would move to the other side of the equation and correct for y prime being too big, would knock it down. So obviously the opposite of that, what we've had before, this is an integrator as opposed to what we call a self-regulator. A self-regulator is one where what I mean by that is a step change in the input, or if the input goes to a constant, then the output eventually goes to steady state. That's what I mean by a self-regulator. So, for example, when I had something like the y prime dt plus a y prime is equal to x prime, say dx prime. Well, notice, again, as I just said, if I rearrange this, dy prime dt is dx prime minus a y prime. Well, that says if y prime it becomes positive, that is the change in y becomes positive, then it gets subtracted off and reduces the derivative. So if it gets too high, it self-regulates by going down. On the other hand, if the change in y is if y prime is negative, so if you go down, well, then if you go down, then that increases the derivative and makes it go back up again. So you can see it's self-regulating. I'll give you an example. Let's look at the house heating example. So if I have rho, so again, I have this house. I have my little house here. I like a lot of windows. Okay, so I've got rho CV hat times volume dt. I'm using theta. Theta dt is equal to, well, I've got the in minus out, so I've got a UA theta minus theta out. Yes. And then I've got the heater. And you can see, let's see, that's the theta dt, and that's, oh, and it's a loss, so it comes in for negative. I'm losing E. So you can see that this is an example where here I have a minus UA theta. So that's exactly like the minus AY prime. Here y prime is theta, and I have a minus UA theta. It's coming in with a negative. So again, it's self-correcting. If it gets too hot in the house, then I start to lose more heat. If it gets too cold in the house, I lose less heat. Let's look at another example. Let's look at the CSTR with a cooler. CSTR mixer with a coolant. So again, here I have got a rho CV hat d theta dt. And that's equal to, well, here I've got the coolant. So I've got UA, and we saw there was an approximation here. So here I can have theta minus the average of theta coolant in and theta coolant out over 2. We saw that was a reasonable approximation there. And again, what you can see here, just like here, is that, and actually let me break this up into 2 terms. So, so let's just break it up into 2 terms. So I've got minus UA theta, and then I've got a plus UA theta 0, theta coolant in plus theta coolant out over 2. So you can notice, so this is rho CV hat V theta dt. So you can note what you can label these things is this is negative feedback. That is, when theta goes up, this makes the theta dt go down. Negative feedback is when the variable goes in one direction and it pushes the derivative in the other direction. That's what negative feedback means. And this is, of course, just an input term. It doesn't depend on theta. Let's imagine, though, that I have a chemical reaction going on in here. So in this case, this is self-regulating. As it is, it's self-regulating. But let's imagine that now I put an exothermic reaction in there. If I put an exothermic reaction, so then I have plus minus delta H times the rate of the reaction. So I can add, which is K0 e to the minus E over R theta times some sort of concentration. If it's first order, or maybe to a power n. So I have this plus minus delta H, K0 e to the minus E over R theta times Ca to the n power if it's like an end-order reaction. And if the reaction is exothermic, if I have an exothermic reaction, then when the temperature goes up a little bit, this goes up, the exponential goes up, and this becomes a positive feedback. That is, here when the temperature goes up, I lose more heat, so that's negative feedback. Here when the temperature goes up, the reaction goes faster and it produces more heat. It tries to heat it up even more. So here's a situation where I have the two negative feedback and positive feedback fighting against each other. This might win, or you might get oscillations. It's possible to get oscillations. So in this sort of situation, you could imagine very easily, depending on the values of the parameters, K0, E, delta H, and UA, that you could get something that oscillates, meaning you could get complex roots of the denominator of G tilde. And depending on whether the real part is negative or positive, it could, if it's negative, the real part, then it can be underdamped, oscillate, decay. But if this reaction is too wild, it could oscillate and blow up. And the whole system could blow up. It all depends on the reaction. So you always have to be careful with exothermic reactions, because, or exothermal reactions, they could blow up. Or are there any questions on that? Okay, so why don't we go on to let's see, series structures. So this was an example, two first-order systems in series was an example of a series structure. Let's look more generally at series structures. So, for example, in a series structure, we have systems that look like, so I could have tau I is equal to dCAI. So if I have, say, CSTRs in series, we already looked at this in the past. So let's have n CSTRs in series. We already saw that each one of these, this is CA in, CA1, CAN. That for each one of these, we can write tau I dCAI dt is equal to, actually I originally write it this way, tau I CAI minus 1 minus CAI minus KCAI. So that was sort of the general form. And if I have a first order reaction. And then when we do the algebra, we had, again, I seem to always do the same algebra 1,000 times. I had dCAI dt, and then I have plus k plus 1 over tau is 1 plus k tau I over tau I CAI is equal to CAI minus 1 over tau I. This thing is 1 over CI. And when I Laplace transform, I have SCAI, let's make these whole times. SCA prime tilde plus 1 over CI is equal to CAI minus 1 prime tilde over tau I. And then this thing just becomes 1 plus STI over TI. And I have CAI prime tilde is equal to TI over tau I, which is 1 over 1 plus K tau I. TI over tau I is 1 over 1 plus K tau I over 1 plus S TI. And this is CAI minus 1 prime tilde. And this thing is what we typically call KPI, the steady state gain. So this is algebra I've done 1,000 times. But notice again that G tilde sub I of S is CAI prime tilde over CAI minus 1 prime tilde. And that's just equal to KPI over 1 plus STI. Now, why am I going through this? I want you to notice that in the series structure, CAI doesn't depend on CAI plus 1. So the reactor, say reactor 2, only depends on stuff to the left, not on stuff to the right. So the information flows from left to right. CA3 does not depend on CA4, it depends on CA2 and CA1 and CAN. So I can notice, and when I can always write GI tilde, G tilde, why don't we say CAN over CAN is equal to CAN over CAN minus 1 times CAN minus 1 is a prime tilde over CAN minus 2. Dot 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 CA2 prime tilde CA1 2 prime tilde CA1 prime tilde CA1 prime tilde CA in prime tilde. Where all I did is I multiplied and divided by the same thing a bunch of times. And this is G overall. And this is just equal to Gn prime tilde, Gn minus 1 tilde, dot 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 G2 tilde, G1 tilde. Where this is just the product of the GI tildes. So what you can see here, and again, this is algebra I've done before, I'm just shedding it, pointing out a few different things. That when I have a series structure where the information flows only in one direction from left to right, then the G overall is just the product of the G's. Nothing too surprising about that because we did that before. Well, therefore, since each of the G's looks like this, KP overall, well, since I'm multiplying these, it's just the product. I equals 1 to n KPI, just the product of the individual KPIs. Well, similarly, B over A, the amplitude ratio. In this case, it's the amplitude of the output over CA in. If I have a sinusoidal input, that's just equal to the product of the amplitude ratios of each of the individual ones. And we know that the amplitude ratio of each of the individual ones looks like this. So this is equal to the product, I equals 1 to n KPI, divided by the square root of 1 plus omega squared TI squared. And of course, if I go through, I could calculate phi, but I'm not sure I want to bother doing that right now. You can certainly do that. The other thing to note is because the G's are the products, notice each G looks like this. So the denominator of G overall is just the denominator is the product of 1 plus STI. Because I'm doing this for 1, 2, 3, etc. So that tells me the zeros of the denominator, which determine the stability, are just S equal to minus 1 over T1, minus 1 over T2, minus 1 over Tn. So if each of the individual ones is always stable, then the whole thing is always stable. Okay, and here was, I had done the algebra about how to get phi. I just see no reason to do that algebra right now. Again, since that's not what I'm interested in at the moment. Are there any questions on that? Okay, so let's just for fun, let's look at a situation. So just for fun, let's look at a situation where I have n CSTRs in series with n goes to infinity, where n goes to infinity, but tau n, tau j goes to 0. So I'm going to look at n CSTRs in series where each CSTR gets smaller, but I get a lot of them, keeping the tau total fixed. Now I'm assuming you had this limit in kinetics, at least for steady state systems. Did you? Did you have this limit? What happens when you have lots of CSTRs in series, each one gets smaller, but the number goes to infinity? Did you have that in kinetics?
We had something like a similar concept as to the residence time, how that sort of changes, or how the conversion changes when you add more CSTRs together.
But you didn't have that limit?
But not this limit.
Okay, because in kinetics you would have it at the steady state situation, not the unsteady. All right, well, we'll do it for the unsteady. Why not? So we're going to do it two different ways. First, we'll do the simple way. Then I'll do a slightly more complicated one, which isn't really much more complicated. The simple one is tau I is just tau over n. So I have n CSTRs in series all the same size. And as I increase n, I make each one smaller. So G tilde overall is the product of each of the GIs. That each of the GIs is KPI over plus S tau I, where tau I is just, or Ti, or tau, well, let's keep it this way. Tau over n. And this is, and since each, actually, why don't I write it this way? So let's, I skip the step. So it's the product I equals 1 to n of KPI over 1 plus S Ti. Now let's keep it no reaction. I can have a reaction or not a reaction, it doesn't really matter. Let's make it just right now with no reaction. So now if each of the Ti's is just, if each of the Ti's is just tau over n, then this is the product I equals 1 to n KPI. That's just a number times 1 over 1 plus tau over n times S raised to the nth power, because I've got n factors. And so let's just rewrite that, make it a little bigger. So I've got this whole thing I'll just call KP. I don't have to keep writing it. So that's KP, and now I have 1 plus S tau over n raised to the nth power. And now I want to take the limit as n goes to infinity. But do you remember this from high school? What's the limit as n goes to infinity of 1 plus something over n to the nth power? Someone has to take their mask down and tell me. I can't hear you when you have your mask on. Good? Okay, again, if I have 1 plus 1 over n to the nth power. As n gets bigger, the power gets bigger. So you would, if this is bigger than 1, it goes to infinity. On the other hand, as n goes to infinity, the thing I'm adding to 1 gets smaller. What's the compromise here? What happens as n goes to infinity? This literally is what you learn in high school. You get E. This is E. And if I have an A here, I get E to the A. That's the definition of E, of the base of the natural number system. So here A is ST. So this is just KP over E to the S tau, which is KP E to the minus S tau. Have you ever seen E to the minus S tau as a G tilde? Have you ever seen E to the minus S tau as a G tilde before? It's on the blackboard. Somebody from this side of the room? Hello, look at the blackboard, don't look down at the floor. Have you ever seen an exponential as a G tilde before? If you don't listen in class, you're not going to learn the material. You need to listen to learn the material. If you want to be a secretary, if that's your goal in life, copy things down. Just copy and don't listen. Then you can be a secretary. If you want to not learn the material, just sleep. But then you're not going to be able to do your job when you get a job as a chemical engineer, and you're not going to last. You should be able to answer a question where the answer's on the blackboard. Plug flow. It's the plug flow reactor. So what we find is the limit, not only in the steady state case, which you should have done in kinetics, but even in the unsteady case, as n goes to infinity, when tau I is tau over n, I have more and more reactors in series, they get smaller and smaller, is the plug flow, which actually makes sense, physically makes sense. Because what happens in a plug flow reactor? In a plug flow reactor, I have no mixing in the axial direction. And I have everything is uniform in a cross-section, but no mixing in the axial direction. Well, you could think of eventually as these get smaller, each one of these becomes like a different cross-section. And there's no mixing, there's only flow, but there's no mixing, no diffusion between one and the other. So each reactor becomes like a separate cross-section. And we see that actually works out. In a slightly more general way, slightly more general, not much. We can notice you need to know a certain Taylor series expansion. The log of 1 plus epsilon, log of 1 plus a middle number. If I expand this in the Taylor series, is minus epsilon plus epsilon squared over 2 minus epsilon cubed over 3 plus dot dot dot. This is for epsilon less than 1. Or actually the magnitude of epsilon less than 1. So that's just a Taylor series you would need to know. We can do the same argument where instead of making all the taus the same size, we can just say tau max for n reactors, tau max goes to 0. So I've got tau i's, what if we say, I have tau 1, tau 2, dot dot dot, tau n, where tau max goes to 0 as n goes to infinity. So that's good enough. I don't really need them all to be the same. And then I can do the same thing. So I can do the same argument, and I can look at the log of G tilde overall. And that's equal to the log of a product. What's the log of the product? Somebody on this side of the room? What's the log of a product? This is a math question. I think it was on the blackboard. What's the log of x1 times x2? I can't hear you. It's the sum of the logs. So, again, I'm going to ask you these simple math questions. I know you know the answer. Now, if you think I'm putting you on the spot, wait until you get a job and you're sitting in front of your colleagues and the answer matters. And your boss asks you a question about something hard, not something easy. So you need to get used to people being able to ask you questions and you answering the questions. Especially when they're something from high school, like what's the log of x1, x2? Okay, so here I have the log of a product. So that's equal to the log of Kp plus the sum of the logs of 1 over 1 plus s tau I. Okay, so this is equal to the log of Kp. And what's the log of 1 over x in the back? What's the log of 1 over x? I can't hear you. What's the log of 1 over x back there? What's that?
Log of 1 minus log of x.
And what's the log of 1?
0.
0, so it's just minus the log of x. So this is equal to minus the sum of the log of 1 plus s tau I. Yes?
What is the difference between this example and the previous example?
This was a special case where the taus are all the same size. Here I can show you get the same result even if the taus are not all the same size, as long as the biggest one goes to 0.
What do you mean the biggest one? What's going to 0 exactly? I'm not sure what's going to 0.
Yeah, I'm taking it n CSTRs in series, but instead of making them all the same size, I allow them to be different sizes as long as all the sizes go to 0. That the result even holds when they're not all exactly the same size. No, it's good to know why we're doing something before we do it. Okay, now as the tau, since the tau i's are going to 0, I can use this result. The log of 1 plus epsilon is minus epsilon plus something else. So this is approximately equal to the log of kb. And now 1 plus s tau I, if the tau i's are going to 0, this thing looks like minus s tau I. A minus and a minus is a plus. S times the sum of the tau i's. And I'm sorry, yeah. Okay, so I think I have the signs backwards. Yeah, it's epsilon minus, right. So then I have a minus sign here, and this, the sum of the logs, just looks like the sum of the s tau i's. And this is just equal to the log of kb minus s, and the sum of the tau i's is tau total. So remember, I'm letting T max go to 0, but tau total fixed. So now I have log of G tilde is the log of Kp minus S tau. So that again tells me that G tilde overall is equal to Kp e to the minus S tau total. That is, I get the same result I got before, but now I get it for the case where each of the reactors is not the same size. It's just they all go to 0 with the total tau being constant. So it's a slightly more general way of getting the same result. And again, what we're saying here is when you have n CSTRs in series, in the limit that the CSTRs all get small, but the number goes to infinity, keeping the total space-time the same, you get a plug-flow reactor, which is very physical, as we said before. Are there any questions on that? Well, let's graph that. If I graph it, and what do I want to plot? I want to plot T over tau and y prime. T over tau, CAN prime tilde. And this is the response to a step input in CA versus T. Now remember, CAN prime tilde over CAN prime is equal to, for a step, it's delta CAN divided by S, because the Laplace transform of the step function, CAN prime tilde, if it's a step, is delta CAN over S. And then here I have and here I have a product, I equals 1 to n, 1 plus STI. And of course here I have KP. So my CAN prime tilde, which I'm going to plot here, is a 1 over S, 1 over 1 plus S tau I. And recall, when n is equal to 1, we know the result. We know that CA1 of t, when I CA1 prime of t, was equal to, went like 1 minus e to the minus t over 10. And then I think there was a coefficient, which I'm not going to worry about. So let's recall what this thing looks like. So obviously for n is equal to 1, it looks something like that. And what happens as n gets bigger? As n gets bigger, it ends up looking more like that, and then eventually like that, and eventually like that, and eventually like that. And this is, in this direction, n is getting bigger. And that makes sense, because if I have a smaller number and I take it to a power, it shrinks more than if I take a bigger number and take it to a power, even when it's close to 1. So something that originally looks like this one is n is equal to 1, it's this one. As n goes up, it looks more and more like this. And the plug flow reactor, if I have no reaction, will look just like this. That's the limit, plug flow. With no reaction. It'll look exactly the same. Where, of course, this is 1, 0, and 1. And again, what does that mean? That means if I have a plug flow reactor in less than tau, if I have a step function at the input, if it's less than tau seconds, I don't see anything at the output, no change. No change. Once I hit tau, I have a step, that step change has worked its way through, so I just get 1. So that's why I get a step function here. How about the over A, the amplitude ratio? So the amplitude ratio, we know, is just this. So it's Kp. So if I use this definition again, that the product of the KPIs is Kp. That's equal to Kp. And now I need the product of each of these denominators when I put in I omega and take the magnitude. Well, that's just the product of things that look like this. Because for each one of those factors, I just get this. And anything else I want to say about that? Yeah. So again, we can look at this. So now the question is, well, what happens here? Let's again look at the limit as n goes to infinity of this thing, where we'll do it both ways. Again, the easy way, where all the reactors are the same size. So A, and then we'll look at it this way. So let's just notice if tau is equal to tau I is tau over n, and n goes to infinity, what happens in that case? Then B over A is equal to Kp times divided by 1 plus omega squared tau squared over n squared raised to the nth power. So I plug in for tau I, tau over n, and since they're all the same, I raise it to the nth power. Another question is, who wins here? And of course, I have a square root, so it's n over 2. So who wins? I've got, as n gets big, this term gets small, but I raise it to a bigger power. Let's see what happens if I do that. So, anything else I want to say about that, Ed? Well, yeah, so you can imagine, you can guess here, we'll do it more precisely here. You can imagine, so what happens as n goes to infinity? As n goes to infinity, not quite sure what to do, so let's look at the log of B over A. That's equal to the log of Kp minus the log n over 2 times the log of 1 plus omega squared tau squared over n squared. So I want to see what that limit is. And now I can use this again. As n gets large, this thing becomes small, so I can consider this thing epsilon. In which case, this goes to log of Kp minus n over 2 times omega squared tau squared over n squared. And here you can see that the n squared wins, because I'm still, once I cancel, I'm left with the with 1n in the denominator. So the limit as n goes to infinity of the log of B over A is equal to the log of Kp. And here, as n goes to infinity, this thing goes to 0. So that tells me then B over A goes to KP, which is just the product of the KPIs. Now, I could have done it this way as well, and there wouldn't have been a big problem. In the slightly more complicated case, I have B over A is equal to KP divided by 1 plus omega squared, and here I have a product of 1 plus omega squared tau Ti squared. To the 1/2. So I just really copied this over. And now I look at the situation where the tau i's don't have to be the same, but where the biggest one goes to 0. So I'm looking at this situation. And the algebra ends up being the same. The log of B over A is the log of KP minus 1/2 the sum of 1 plus omega squared Ti squared log. And again, as long as the maximum of the tau i's goes to 0, this just goes to the log of KP minus 1/2 omega squared Ti squared. And I've got a sum of terms. And each of the Ti squares, let's see, so that's the sum of n of them. And what did I want to do with that? Actually, I didn't want to bother going through this. So I'm going to leave this out. I wasn't planning on doing that. Just the A was good enough. This one was good enough. So over here, we have our result, and let's just plot what this looks like. So here I'm going to plot Kp and 10 to the minus 3. And what I'm plotting here is the log of the amplitude ratio, or log of B over A versus the log of omega tau over n. And omega tau over n. And this goes down. And this is the situation, in this case, the curves are going to increasing n. And what you can see is that as n gets large, as n goes to infinity, the answer goes to Kp. Well, notice as n gets large, then as n gets large, this thing gets smaller. So for any given curve, as n gets large, I move to the left. So as n gets large, for any given curve, I move to the left. So I always go to Kp. And the bigger n is, the quicker I get there, because I'm closer to the limit. So that's how you sort of see what goes on. And moreover, we know that for first order processes in series, this B over A, which is, where's B over A? Here it is. We see that each one of these factors for any omega is always greater than 1. So when I have a lot of factors, each one of them is greater than 1, then that tells me this whole thing is always less than Kp. And the more factors I have, the more less than Kp it is. That's why it goes down. Because as omega gets big, the bigger omega, the bigger the denominator is. So they always go down to the right. Are there any questions on that? Questions? Okay, now again, hopefully when there are no questions, it means you understand what's going on. If you've tuned out and there are no questions because you've tuned out, that's no good because then you're not learning the material. Again, the reason to come to class, and I see a number of people haven't come to class, so I'm going to have to do the attendance sheet again. The reason to come to class is to try to learn the material in class, not to copy everything down. You'll get the photos. There's no reason to copy. What you should do is try to listen, and as this gentleman did, when I was doing a calculation and he didn't know why I was doing it, he very correctly said, "Why are you doing that calculation?" That's a perfectly valid question. In fact, that's the most important question you could ask. Before you worry about the details of the algebra, why the hell are you doing that? That's a very good question. Thank you for asking me. If you don't know why I'm doing something, ask me. Ask me, that's why I'm here. Otherwise, I'll just tell you to read the book. You're here in class to try to learn, and the first thing you need to do, before you can learn what the answer is, you have to know what the question is. An answer without a question is not very useful. So you always need to ask yourself, why is that guy in the front of the room with the chalk writing this algebra on the blackboard? Why is he doing it? If I don't know why he's doing it, the answer doesn't mean anything to me. So don't be shy to ask questions. Even if they're, especially if the question's like, what's going on? I don't know what's going on. That's a valid question. Okay. Any questions? I'm going to do a little erasing. Notice over here in these series structures, I call these non-interacting because obviously they interact and the information goes from left to right, but nothing goes from right to left. So reactor 2 only depends on reactor 1. Reactor 3 only depends on 2 and 1. It doesn't depend on 4. That's called non-interacting. It's not strictly non-interacting because it doesn't, what non-interacting means, it doesn't interact to the right, it only interacts to the left. So now I want to look at interacting. Now, again, I want to stress what happens in non-interacting systems. Non-interacting systems are somewhat boring. I hate to say something this class would be boring, but in the sense that the overall G is just the product of the individual G's. The overall amplitude ratio is just the product of the individual amplitude ratios. So that's not all that exciting. Moreover, the stability, there are the same roots of the overall G tilde as there are of the individual G tildes. They're all -1 over T1, -1 over T2, etc. Nothing different. Once I do interacting, all that goes out the window. So let's look at interacting system. And let's imagine an interacting system as I could have a bunch of tanks that are hooked up. So this is, say, solid. And I have some fluid here. And I'm going to have the height here as y1 prime tilde, or y2, y3, etc. And I have some sort of inlet height x. So is it clear? I've got a bunch of tanks that are hooked with a pipe on the bottom. Maybe I should make this a little lower so it looks more like it. So I've got a bunch of tanks here, and they're hooked with a pipe. So what happens? If this height goes up and is higher than these heights, then fluid flows from the higher one to the lower ones by basically hydrostatics. So if I look at, say, dy1 dt, well, that's equal to some and y1 times the cross-sectional area, A1. So this is the volume in this tank, ddt of the volume. Well, it can be K1 times x minus y1. In other words, if this one is higher than this one, it'll make y1 go up. Otherwise, it'll make y1 go down. And then I have a minus K2 times y1 minus y2. So if y1 is higher than y2, it loses, it goes down. If x is higher than y1, it goes up. Is that clear? And similarly, if I do the same thing for y2, I have a2 y2 dt. That's equal to k2 times y1 minus y2 minus k3 y2 minus y3, etc. So where the k's have to do with the fluid mechanics, the rho g's and the etc., which I'm not going to fuss about here. What you notice here is this is interacting because the height of y2 depends not only on y1, it also depends on y3. Height of y2 depends not just on y1 and y2, but also on y3. So the information flows in both directions. Everything's hooked up. Okay, so I would like to introduce some sort of notation consistent with your book, which is somewhere there's some notation. Instead of A's, they call them H's, but otherwise everything's the same. I don't know why they call them H's instead of A's. So I'm going to call this an H instead of an A, where H is the cross-sectional area. And let's notice that certain things are going to have units of time. So notice if I take h1 over k1, if I divide through by k1, then this has units of height. If I divide through by k1, this has to have units of height. Well, y is units of height, so if I have time in the denominator, I'll have a time in the numerator. So I'm going to let ti be equal to hi over ki. And that has units of time, so these are time constants, just by dimensional analysis. Okay, are you with me? So what's the goal now? Before we launch into all this algebra, first I'm going to make all the variables primes, and then I'm going to calculate the Laplace transforms. So make them all primes. And now there's a lot of algebra. So before I do the algebra, you need to know where I'm going, why I'm doing it. Here I wrote out the model. Just as in the non-interacting system, I went through the algebra and I calculated G tilde. I found the G tilde. I would like to find the G tildes here. So that's what I'm going to do. And remember, how do I calculate G tildes? Yes?
Sorry, I just remember us using that the change in height was k times height raised to the 1/2. I'm just curious as to why we aren't using that law here.
Good question. If you remember earlier in the semester, when we had, right over here, if I have a tank and it's open to the atmosphere, then the fluid that goes out, the flow rate, V, is equal to some constant times the square root of L, approximately. And that came from Bernoulli. What was going on here is this was exposed to the atmosphere. And there Bernoulli applied, and also the height really Bernoulli applied because it was exposed to the atmosphere. Here, rather than this being a Bernoulli problem, this is a hydrostatics problem. And a hydrostatics problem, if you remember from the beginning of fluid mechanics, 341, there's no air, it's just all the same fluid. So it's like a manometer. In a manometer, the height, it just depends on the difference in heights and the difference in pressures. And if up here, this is all exposed to the atmosphere, there's no difference in pressures, so the flow just depends on the difference in heights. Okay? No, it's very good that you asked that question. That's also, those are really good if there looks like there's a contradiction with something we did before. Okay, so again, what we would like to do is we would like to solve for the G tildes. Yes? Yes, it's exactly. I write out the equation. The initial condition, I assume, I just subtract the initial condition. I subtract what's the equation at t is equal to 0, and then I get primes. That's exactly how I do it. I subtract what was going on at t is equal to 0. And that just guarantees that my initial condition on the primes is 0.
So you're saying that you've done that like theoretically, you're just not sure.
Correct. Well, I did it earlier in the semester.
You're not just saying like, oh, we just make these products.
No. You're absolutely right. No, it's I did it earlier in the semester, and we showed how to do it in general. So since we know how to do it, I'm just assuming that it's been done. Other questions? So again, what I want to do is I want to get G tilde. And remember, G tilde is for each output and each input pair. So I'm going to look for a G tilde of the output y1 tilde in terms of x prime tilde and also in terms of y2 prime tilde. These are the two guys that influence y1 prime tilde. When I look at y2 prime tilde as an output, that's influenced by y1 prime tilde and y3 prime tilde. So I'm going to get a whole bunch of G tildes depending on my choice of output and my choice of input. This is all the warning of before I launch into the algebra. Okay, so ready? We're going to do some algebra. Before I do algebra, I want to get rid of all the h's, so I'm going to divide by k. Divide by k1, and this becomes 1 over t1 dy1 prime tilde dy1 prime dt. Plus, when I divide by k1, I have x prime minus y1 1 prime minus k2 over k1 y1 prime minus y2. So all I did now is I divided by k1. Now I'm going to take a Laplace transform. And I'm going to move all the y1 stuff to the other side of the equation. So I'm going to have a y1 prime tilde times 1 over t1 plus 1 from here plus k2 over k1. And what's left on the other side? On the other side, I've got x prime tilde plus k2 over k1 y2 prime tilde. So I have y1 prime tilde is equal to x prime tilde times 1 over 1 plus k2 over k1 plus 1 over t1 plus something times y2 prime tilde. And here I have a k2 over k1 divided by 1 plus k2 over k1 plus 1 over t1. And notice, here I have y1 prime tilde in terms of x prime tilde and y2 prime tilde. These are the forcing functions. These are what's driving y1 prime tilde. And I lost an s somewhere. This was s times s over t1, not 1 over t1. S over t1. When I take the Laplace transform of the derivative, I get an s, so I have s over t1. And this thing is g tilde for how x prime tilde influences y1 prime tilde. And this thing is g tilde for how y2 prime tilde influences y1 prime tilde. Is that clear? Just make sure I don't want to do anything, if I want to do anything else there. That one is sort of straightforward. Okay. Now, by the way, I can multiply and divide by t1. So if I multiply it top and bottom by t1, I've got a t1, and then here I'll get a t1 here. Do I want to do that? I have a certain form in my notes, and let's see if I want to get that form. I think I have too many y1s. Let's just see what's not agreeing with my notes. Okay, I set up the problem differently. Okay, so I'm going to have to go back and set up the problem slightly differently than I had in my notes, than I had here. So x is not going to be the height here, but I'm going to make x the input. X is just the input. And if x is the input, then there's no y1 prime tilde here, because x is just the input. So the way I chose the problem before wasn't correct. It's x is just the input, and do I want this to be k1 or k2? Sorry, I should have looked at my notes instead of the problem. Yeah, and I want this to be k1. So I'm going to have to redo this. K1. All right, so this is, and this is k1. So let's just fix all that. And I will fix this. And that'll will end up being everything we can do today. G tilde of x to y1 prime. X prime to y1 prime. So let's go through and do it again. So over here, okay. So let's do it line by line, and then we'll. So again, the cross-section, the change in volume of tank 1 is due to the input, which here is just going to be x prime as an input, and minus k1 times y1 minus y2. Okay, so now I'm going to again divide by k1. I can certainly divide by k1. That gives me 1 over t1 here, and here I get 1 over k1 here. And I get no coefficient here, because I divided by k1. No coefficient. Now, I again move everything to this side of the equation, all the y1. So here I have a y1 prime tilde, that's a 1. And here I have plus s over s times t1, because h over k is t1. 1 plus s t1. H over k was t1, so t1 should be in the numerator. And what's left over here? Here I have a 1 over k1 here, and no coefficient there. 1 over k1 and no coefficient. So now I can go through and do it. And now notice here I have 1 over k1 times 1 plus st1. And here I just have 1 over 1 plus st1 when I divide this out. And now I have the g tilde for how x prime influences y1 prime tilde, and how y2 prime tilde influences y1 prime tilde. So I was doing a different problem before. Now I did the right problem, the problem I wanted to do, where instead of x being a height, x is just an input. And what you can see here is we get y1 prime tilde in terms of the things that influence it, x prime tilde and y2 prime tilde, where we can think of g tilde x prime to y prime tilde as the ratio of y prime tilde over x prime tilde when y2 prime tilde is 0. So then this one would be 0, and I'd just be left with this. Similarly, g tilde of how y2 prime tilde affects y1 prime tilde is in the case where x prime tilde is 0. So this would drop out, and I would just get this. Are there any questions on that? We still have 5 minutes, so not that far out. So again, we wrote down the model. We wrote down what's the equation for y1 prime tilde. And we took the Laplace transform and solved for the g's. Let's look ahead what we're going to do. We're going to do the same thing for this. And when we get the g's, then we're going to look at, what do we look at from the g's? We're going to look at the stability by looking at the roots of the zeros of the denominator. So we're going to look at the stability, and then we're going to look at the amplitude ratio as well. And we're going to look at the stability, the amplitude ratio, and even phi. So what's the first step before we do that? First, we have to get the g's before we can look at these effects. So again, just the first step is I can divide by k2. And that will give me t2 dy2 prime dt. And then when I divide by k2, I'm just going to have a 1 here, so I'll have a plus 1. Plus y2 prime tilde. y2 prime. Times 1 plus k3 over k2. So what did I do? I divided by k2, and then I moved this to the other side. That gave me the 1. I divided by k2, and I moved this to the other side. And what's left on the right? What's left on the right is equal to y1 prime tilde plus k3 over k2 3 prime tilde. So all I did is I divided by k2 and moved these two terms to the other side of the equation and left what's there on the right. And when I take the Laplace transform, then this is going to give me y2 prime tilde times st2 plus 1 plus k3 over k2 is equal to, and I didn't have any tildes here, it's just y1 prime, y1 prime tilde plus k3 over k2, y3 prime tilde. I know what y1 prime tilde is. And I don't have time to do that today because I have only 1 minute to go. But just so you know what we're going to do next. What we're going to do is then we're going to take this and plug it in here for y1 prime tilde. And notice that's going to have another y2 prime tilde in it. So I'm going to have to move that y2 prime tilde to the other side of the equation. And I'm going to solve for y2 prime tilde in terms of x prime tilde and y3 prime tilde. So I'm going to solve. So I'm going to plug in, and then I'm going to solve for y2 prime tilde in terms of x prime tilde and y3 prime tilde. So that's where we're going, and we'll get those g's, and then we'll learn something about y2 prime tilde. We'll learn about the stability of y2 prime tilde, and we'll learn about the amplitude ratio. So the amplitude ratio, again, could be x coming in as a sine wave. Are there any questions? Questions? Okay, once we finish this chapter, we'll have an exam.